Good day everyone. Today I'm going to show you a step-by-step procedure to deploy a machine learning model on a low-power embedded system such as a microcontroller. This is what we call a TinyML, a tiny machine learning, which highlights the intersection of the machine learning techniques with embedded systems deployed in real time for specific application. This will only bring the intelligence a little bit closer to the data source. Various applications are possible, such as predictive maintenance, like monitoring and predicting the industrial machinery. It could be used for health monitoring, environmental sensing, gesture recognition, and so on. However, the application for today will be to detect engine knocking or abnormal vibration, and this will be applied to a 20-year-old Toyota RAV4 engine. So the machine model we will be using today is the k-means clustering technique. We will be deploying the anomaly detection model directly on an embedded system, which is the Raspberry Pi based 2040 Connect. This low profile nanoform microcontroller has a 133 MHz dual core processor. Also, it has a 16 megabyte flash memory. It has the micro USB plug and play and various interfaces such as the I2C, I2S, UART and SPI and so on. It does have a Wi-Fi module, the Nina Wi-Fi, and a Bluetooth as well. Yet a small Arduino microcontroller, but it has 8 analog outputs. It has 22 digital pins, 20 of which are supporting pulse width modulation. In addition to this, and most importantly, it has a microphone. This is a microphone here. And a 6-axis inertial measurement unit. This chip will be able to provide us with acceleration values along the X, Y, and Z, together with the gyroscope data on the X and Y and Z as well. Now, one question you may ask yourself, is any Arduino-based microcontroller suitable for the deployment of machine learning? Now, the answer for this is really not, because you have to look at the computational power, because TinyML models are designed to run efficiently on microcontrollers with limited computational resources. So you need to look at the Arduino boards with microcontrollers that have sufficient processing power and memory to execute your machine learning model. The other aspect you should look at is the compatibility. You need to check whether the Arduino board you are choosing is compatible with the TinyML framework and libraries you intend to use. For example, most popular TinyML frameworks, such as the TensorFlow Lite or the Edge Impulse, they really provide support for a limited range of boards. Whilst some Arduino boards offer expansion capabilities through add-on modules and shields and external sensor connections, it will be useful if you can choose an Arduino board that supports the sensors you're trying to use for your application. Of course, you need to look at other factors such as power consumption, cost, and most importantly as well, it will be nice to have a board that is supported by documentation, tutorials, and has a community support as well. The most popular Arduino boards for TinyML deployment, mainly the Arduino Nano 33 BLE Sense or the Arduino Potenta H7. Even though that the RP2040 Connect is not on the main list, but we will be using this together with Edge Impulse, and we will show the deployment of a machine learning model and how it is applied for the engine knock detection. We are only interested to find whether the engine is running normally or abnormally. We are not really interested in the characteristics of the abnormal operation if it exists. I only need to find out, is it normal or not normal? Anomaly detection algorithms can vary from various techniques. So using k-means is not the only one. You could use the local outlier factor, isolation forest, and so on. You can also use the classification models such as the support vector machine, or maybe random forest or neural network. All of these can be trained to directly classify engine operating conditions as either normal or there is an indicative sign of a knock. So the procedure will be as follows. So first, we're going to collect data using the Raspberry Pi 2040 Arduino Nano microcontroller, and the application will be to measure the vibration of a running engine at a normal operating temperature. Then we're going to take these data and then import them to Edge Impulse, and we will process the data, and then we will create and train our model there, and then we're going to deploy it back to the Arduino Nano RP2040 Connect, where we will apply it again to the engine to see whether it is successfully predicting a knock or a vibration. In order to mimic a knock or a vibration in the engine, we will replace an existing healthy coil with another faulty coil, and hopefully we will should be able to detect this anomaly. First, we need to connect the Arduino microcontroller to a computer. In order for the Arduino microcontroller to be recognized, first you need to install the Arduino Embed Operating System Nano Boards library. So once you install this, you will be able to see your Arduino Nano RP2040 Connect. Now the Embed is a fully preemptive real-time operating system, meaning that you can run multiple programs at the same time, much like what happens in your notebook or smartphone. For you to do that, you have to go to the board manager and then type in the Arduino Embed Nano board, and then you make sure you install this. Make sure you install the latest core version. For the cloud editor, the Arduino Create agent has to be installed for the board to be recognized. Now the updated libraries are installed. Hopefully your computer should recognize your Nano Connect by looking at the port. You're going to see that there's a port number associated with your device. Now if this is not the case, then you have to try the bootloader mode. This is by tapping the reset button twice, then uploading a blink sketch, and then you press the reset button once again. Hopefully by uploading the sketch, it should be able to recognize the port. If this doesn't work, you can try the hard reset by connecting a jumper wire between the ground and the rec pin. If this doesn't solve it, you may have to go to the factory reset, but in any way I recommend that you use Windows 10 and above. I had similar issues with Windows 8 and previous versions. Now if you reach this stage, then you can upload an example, a blink example straight away, just to check that all is okay, your PC is recognizing your hardware, and communication is good to go. So if the blink example is running okay, the next step is to collect some real-time data from an engine. So first we're going to connect this to a PC, and then we're going to put the Nano RP2040 on the engine, and then we will record a normal operating vibrations, and in the hope that if we create later an abnormal vibration, that should be detected by the machine learning model that we will train in the edge impulse. In order for us to collect the data from the car engine, first we will run a simple Arduino code. This code will enable us to collect the data from the accelerometer and the gyroscope onboard the Arduino Nano Connect. We will be also using a third-party software, the CoolTerm, which will convert our data using the serial communication straight away to an Excel file. This program starts by including the necessary library, the LSM6D SOX. This is a library designed for the Nano RP2040 Connect. We then declare the variables to store the accelerometer and the gyroscope data. Inside the setup, first we initialize the serial communication with a baud rate of 9600, and we will wait for the serial connection to be established by using the while serial. Then we will initialize the IMU, the inertia measurement unit sensor, by using the IMU.begin. If the initialization fails, it prints an error message and enters an infinite loop. Now in the main loop, we first check for if the data of the accelerometer is ready by using the IMU.acceleration_available. And if the data is available, we read those data, and this is done in a similar way for the gyroscope component. If you notice that the data is printed in a comma separated format by using the serial print comma, this makes the data easier to parse and process if needed. For the CoolTerm, you need to go to the options and make sure that the COM port is defined that is associated with your Nano RP2040 Connect. So if the port is not shown, make sure that your Arduino is connected. Now I'm connected mine again to check. If you still can't find it, just cancel it and simply click on options again. Alright, so this is COM4. This is our Arduino Nano RP2040 Connect. So we just click OK. In fact, you could define where would you like to save your folder. You can go to the file capture. You could define the name of the file and the name and the format. If you click on the connection, go to capture to text binary, click on start. You can name your file. In my case, I'm just going to call it test2.csv. Simply click save, and in this case the file is ready for you. You only need to connect to get the real data. So now we are collecting data while the Arduino is on the desktop. We will take this Arduino later to the car engine and get real data from the engine vibration. Once you are done, you can go to the connection, go to File, Stop, then you can click on Disconnect. So we have collected data both when the engine is running and when the engine is at rest. So the first file is when the engine is at rest, and the second one when the engine is running. Both are labeled as normal data, where 20% of the data will be used for testing, which is shown in the third file. Here's a sample of one of the files. If we investigate this further, we will be choosing a couple of values first. So if you look at the caption, you will see that the light blue is the acceleration along the X, orange is acceleration along the Y, gray acceleration along the Z. The yellow, the dark blue, and the green are the gyroscope data on the X, Y, and Z respectively. If you look at the light blue and the orange, they are a little bit behind each other and almost zero. So the acceleration along the X and Y were not very clear here. Whereas the gray one, which is the acceleration on the z-axis, is almost having a value of 1. This indicates 1g, and this is normal, and this is what we are expecting due to the Earth's gravity. Having said that, this doesn't mean that there are no slight oscillations around those values, which will be our interest later using the spectral analysis tools. If you look now at the gyroscope data, the gyroscope data on the x-axis and the y and the z, they are all very clearly oscillating, and values could reach around maybe 12 degrees per second and so on. We will now take those data to edge impulse.